Good morning, students. I welcome you all for another lecture on the course Computer Architecture and Organization. From this class onwards, I am going to discuss about the processing unit, which comes under Unit 6 in our syllabus. In this class, I am going to start my discussion with the first concept, that is the fundamental concepts. Right, straight away we go on entering into our concept. A processor fetches one instruction at a time and perform the operation specified. What's the meaning of this? We know that at a time a processor can execute only one instruction. Before execution of an instruction, first what a processor can do is it fetch the instruction from memory, because the instructions of a program generally stored in memory. So that first the processor fetches the instruction and later it will execute the instruction. So at a time a processor can execute only one instruction. That's the meaning of this. Once we fetch an instruction, we receive that instruction from the memory. Before execution of it, we decode the instruction. In the decoding process, we identify that what the operation and what the operands are. And according to the operation, we can perform a particular task in the execution of an instruction. So that is the meaning of first one. The instructions are fetched from successive memory locations until a branch or a jump instruction is encountered. That means, let you can assume this is a program. This program has these other set of the instructions. Generally, this set of instructions of program may store in the memory in successive memory locations. But your processor can execute one instruction at a time, irrespective of the number of instructions present in a program. So your processor start execution of first instruction. First it will fetch this instruction. After fetching it, decode, and later it will execute it. And then it will go and execute the second instruction. Before execution of second, first it will go and fetch that second instruction from the memory. Later it will go and execute it. That means your processor can fetch the instructions from successive memory locations. There is no doubt at all. This sequence can changes only when the instruction which was present in your program belongs to either jump or it belongs to branch. We can call jump and branch and jump both are same. So here the meaning of this one is the instructions are fetched from successive memory locations until a branch or a jump instructions encountered. Once here I have a branch instruction, that means here I have a jump instruction. Let you can assume this program is start from a location some 2000 H of our memory. And here I have a branch instruction, that is JMP some 3000 H. Once your processor comes to this instruction, what it do? In execution of this instruction, it change the program execution sequence to a location address which is a 3000 H. So here, this is the meaning of this particular statement. That is, instructions are fetched from our successive memory locations until a jump or branch instruction was encountered. Once you have a branch instruction which exists in your program, it may present it somewhere else. No doubt, it will change the execution sequence of your program. So that's the meaning of this. The processor keeps track of the address of a memory location containing the next instruction to be fetched using a register which is called a program counter. The meaning of this particular statement is, if the processor want to execute this instruction one by one, it will fetch these instructions one after one from the memory. In the particular process, your processor took the help of an important register which comes under machine accessible group, which here we can call as a program counter PC. The job of this PC is, obviously it will point the address of the next instruction from where your processor going to took the next instruction from the memory. So that address is always provided by the program counter PC. So in the execution of successive instructions, we took the help of a program counter PC because the job of that program counter PC is always it will provide the address of a next instruction. And here we took the another important register involvement in execution of every instruction, that was a instruction register IR. What's the job of this? The basic function which is performed by instruction register IR, it is also comes under machine accessible group. The job of this instruction register IR is this register holds the instruction which is executed by the CPU. What are the instruction your CPU going to execute? After fetching your instruction, fetching means bringing the instruction from the memory to the CPU. The instruction fetching is over only when we can say that the instruction which we are reading from the memory was copied onto the CPU register, which is instruction register IR. The job of instruction register IR is this register can hold whatever the instruction your CPU can go and execute. So here we took the help of a program counter PC and instruction register IR. We are going to execute the programming instructions in a sequence. That you have to remember. Next, fetch the contents of memory locations pointed by the PC. The contents of these locations are loaded into instruction register IR. So here I would like to give an example for better understanding of a concept. Here my assumption is I am going to execute a program. The program have a set of instructions. Each and every instruction size is equal to 4 bytes. Here my assumption is each and every instruction in a program is equal to 4 bytes. And my memory is byte addressable. You have to keep in your mind this particular one. That is, instruction size is 4 bytes and memory is byte addressable. So if I want to execute a program, what I have to do? This is my program, and this program, each and every instruction size is 4 bytes. In the execution of an instruction, what are the different steps I can follow? So if I think in that direction, my first step is fetch the contents of memory location pointed by the PC. The contents of this location are loaded into the instruction register IR. That means whatever the address our PC can point it of a memory location where I have an instruction, I can go and fetch the instruction from that PC pointed location. The fetch instruction was copied onto instruction register IR. That means I can say my instruction fetching is over only when I can go and bring the instruction from memory to CPU. It was copied onto instruction register IR. So my first step is fetch the contents of memory location pointed by the program counter PC. The contents of this location are loaded onto instruction register IR. I can represent that is in terms of RTL statement. It is like this: the content of a PC specified location. The contents of a PC specified location, that's the meaning of this, was copied onto instruction register IR. This is the first step what I have to do in execution of an instruction. And coming to the second, assume that the memory is a byte addressable, that's what I am already told to you, and increment the content of program counter PC by 4. Why? I increment program counter by 4. I have already clearly told you guys, that is, an instruction size is 4 bytes. If I fetch this instruction, basically this instruction occupies 4 locations. Let you can assume this program is start from a 2000H. My first instruction occupies 4 locations. The first location 2000, 2001, 2002 and then 2003. My second instruction was stored on the location 2004H. If I fetch the instruction which was present in a 2000, next my PC go and point the next instruction which was available from a location 2004. So that here I increment PC content by 4. Here my PC content is 2000. By execution of this particular statement, that is in brackets of PC plus 4, that means PC value is 2000 plus 4. Now the resultant is 2004 that was copied onto program counter PC. Then my PC points this instruction. That is my second step. This is the step number 2. And my third step is carry out the actions specified by instruction in the IR. So what are the instruction I have in the IR? That instruction, what are the operation it can specify? We have to go and perform those operations. So here important thing is the first 2 steps, that is the fetching of the instruction from the memory, whose address is appointed by the PC. Later I have to go and increment PC content by 4 to point the next instruction. These are 2 things what happen in fetch cycle or fetching operation. In execution operation, what happens? What are the instruction I have in instruction register? According to that, I have to go and carry on my operations. So this is a step that is related to execution of an instruction. That you have to remember, friends. Next. So in order to execute that instruction, this is a data path. What a data path is? So here the data path. So what a data path means? Data path means different internal registers of a processor and the internal bus along with ALU we can call as a data path. Data path is nothing but it is a collection of internal registers, internal bus and ALU of any central processing unit we can call as a data path. So with the help of this data path, how we can go and access the information from the memory and how my CPU go and perform the operations internally. See here, friends, I have only one internal bus. This bus was present internal to my CPU or internal to my processor. Depends on the word length of the processor, this internal bus with depends on it. So here I have a different registers. This is a program counter PC and this is MER register, memory address register, and this is MDR, memory data register, and sometimes the same register we can also call as MDR, means memory buffer register. With the help of these 2 registers, that is MER and MDR, my CPU or a processor can communicating with the memory with the help of address lines as well as data lines. So here important thing is, if you are observing or not in this diagram, this MDR have a bus connection, that is a bidirectional bus connection exists. It is connected to internal bus as well as it is connected to data bus. Why it is bidirectional? So here that's what I mean. MDR has 2 inputs and 2 outputs. 2 inputs and 2 outputs in the sense its a direction is a bidirectional. Its a direction is bidirectional. So if you go for this is one output and this is one output. So there are 2 outputs and there are 2 inputs. This is the one input and this is the second input. So that is the meaning of this particular statement. MDR has 2 inputs and then 2 outputs. So my processor can communicating with external world with the help of a machine accessible registers, that we know that. Here my processor can communicating with the memory with the help of a pair of registers. One is MER and second one is MDR. What MER is? MER is memory address register and MDR is memory data register. The job of MER is always it holds the address of memory location which is right now communicating with the CPU or with the processor. And the job of MDR is, this is a register can hold the data which is transferred to or received from MER specified location. So that my processor can communicating with the memory only with the help of MER and MDR registers. And MER is directly connected to my address bus and MDR is directly connected to a data bus. So this is my program counter PC. So here one interesting thing is, generally your PC can provide the address of a next instruction, but a PC generated address can't directly transfer to the memory with the help of an address bus. Here what happens is, what was the address your PC going to generate to go and fetch a next instruction from the memory? The generated address was a transfer to a register MER. Later MER transferred that address to the memory with the help of this address lines. So that is an important thing. Once the address we are transferred to the memory, and later you send the control signals to your memory. That is, my task is you go and read an instruction from any specified location, so that once I send an address, later I send a control signal, that is a read, then your memory plays the location instruction on the data bus that can be collected by MDR. But the instruction not there in this MDR, finally it will be transferred to our instruction register IR. It is like this. Instruction register IR. Here important thing is this particular one, that is instruction decoder and control logic, which will generate whatever the control signals that are necessary to communicating with the either external world or in order to do a different operations internal to your central processing unit. All these control signals are generated by this instruction decoder and control logic. That's why the output of this instruction decoder and control logic is purely a control signals. This control signals is not only useful for me to do different operations internal to my central processing unit, these are also helpful for me to communicating with external world. That means whenever I want to communicating with the memory or whenever I want to communicating with an IO devices, definitely I need a control signals. Those control signals also generated by this instruction decoder and control logic. So that's why here I used a different color for representation of that. You have to remember that. And next here I have a different registers are exist. So one is a Y and another one is Z. This Y and Z I can call purely machine accessible registers, or simply I can call these are two are my temporary registers. These are two registers are very useful for me to do any operation by using arithmetic and logical unit. So if you are observing or not guys, here there is a multiplexer. The multiplexer output is given as one of the input for my ALU, and the second input for my ALU is which was connected from an internal bus, which I treated as input B. Input B. So according to again the control signals what I was applying to ALU. So based on the control signal, this ALU can perform operation on inputs A and B, and it will produce a result that is temporarily copied onto register Z, and later it will be placed onto the internal bus. There it will be transferred to, it is belongs to the internal register, it goes to internal registers of my CPU, or the produced results was belongs to external world, again it will be transferred to external world with the help of this data lines. So that is an important thing. But here another interesting thing is, there is a constant 4 which is applied as a second input for my multiplexer mux. So one input for this mux is the output of register Y, which is my temporary registers in my central processing unit, and the second input for my multiplexer was a constant 4. What this is? I already told you guys, that is in my system my instruction size is of 4 bytes. My instruction size is of 4 bytes. If I want to access the next instruction from the memory, the PC value must be incremented by 4. That task also done by this program counter PC. Through this register Y, I transfer PC value as an input to this ALU, or I can transfer this PC value directly to ALU as a B input. If I want to do increment PC value by 4, then like at one point the next instruction, I need a second input for ALU was of 4. That 4 I was transferring from a multiplexer output. So here the multiplexer input was a constant 4. By selection of this particular constant 4 input, I transfer the constant 4 to the second input for ALU. So that is the use of this particular one. And here a set of registers, that is R0 to Rn-1. These are registers I can call as either GPRs, or these are registers I can call as SFRs. That means these are group of registers. Here I have total n registers, and these registers are either general purpose registers or these registers are special function registers. So with the help of this data part, I can do different operations internal to my CPU once I was fetching the instruction from the memory. So that is the thing you have to remember regarding to this particular one, that is a processor organization of a data path inside of my CPU or inside of my processor. Next, execution of an instruction. Transfer a word of data from one processor register to another processor register. So, what is the meaning of this executing an instruction? Once we fetch an instruction, in the execution of an instruction, there is a chance or there is a possibility the doing operation belongs to any one of these four. Any one of these four. That means in executing of an instruction, in that execution process, what the operation was? That operation belongs to any one of these four. What the first one? Transfer a word of data from one processor register to another processor register or to ALU. So in execution of an instruction, my operation is transferring of a data from one CPU register to another CPU register, or I may transfer a content of a register to ALU because to do some arithmetic and logical operation. And the second one is perform an arithmetic or a logical operation and store the result in a processor register. This may be a second possibility in execution of an instruction. Either I can go and perform either arithmetic operation or I can go and perform a logical operation on the input values. After performing of arithmetic operation, the result can be stored in one of the internal CPU registers. That is the second possibility. And coming to the third possibility, fetch the contents of a given memory location and load them into processor register. That means I would like to go and take a data from a memory location. That location data was transferred to one of my CPU register. And one more thing is, store a word of our data from a processor register into a given memory location. I would like to give an example for all these things. For example, first one is transfer of a word from one processor register to another processor register. That means your my operation is just, I assume that move some not comma R1. Here my instruction is move not comma R1. What is the meaning of this? Move one of my CPU register R0 to another CPU register R1. That means whatever the word that was present in a CPU register R0, that is a simply transfer to R1. So in this instruction execution, what I was doing internally, I was doing an operation that is transferring of a word of data from a source register R1 to a destination register R1. So here R0 and R1 both are my CPU registers which exist internal to my central processing unit. And coming to the second one, performing of an arithmetic or logical operation and store the results in a processor register. For example, my instruction is like this: add R1 comma R2 comma R3. This is my instruction was. By using this instruction, I do addition between the content of a register R1 with R2. The produced result, which is our sum, was transferred to another processor register or CPU register R3. And similarly, I can go and do XOR operation, XOR R2 comma R3 comma R4. The meaning of this one is do logical exclusive or bit by bit between the content of register R2 with R3. The produced result was transferred to another CPU register R4. In execution of that add instruction or XOR instruction, what my internal operation is like this. Either I can do either arithmetic operation or I can do a logical operation. That is purely depends on what the instruction I'm going to execute. And coming to the third one, fetch the content of a given memory location and load them into a processor register. For example, here my instruction is load 2060H in brackets comma R1. The meaning of this particular instruction is load register R1 with the content of a memory location 2060H. That means go and read a word of data from a memory location whose address is 2060H Later the reloaded data is copied onto one of my CPU register, which is R1. And coming to the fourth one, which is opposite to the third, that is store a word of data from a processor register into a given memory location. That means here my operation is store. My instruction here is a store. Some R2 comma in brackets of 3000H. The meaning of that one is store the word what was existing a CPU register R2 into a memory location whose address is 3000H. That means that based on the instruction, the internal operations are performed. Those internal operations belongs to any one of these four varieties. Either the data was transferred between two registers of a CPU, or between a register and ALU, or doing of arithmetic operation or a logical operation between the inputs of ALU, or the third thing is go and read a data from a memory location. Not only think I'm going to read a data only from the memory location, sometimes I can go and access my data from an input device. So here I can improvise my statement. Here I can go and fetch the contents of not only given memory location, it is also from an input device. An input device. Sometimes I can go and read a data from an input device. And similarly, the last one, I'm not only store my result to a particular memory location, sometimes I have to go and send my results to an output device also. So again, I improvise this statement. I'm not only transferred the word to the memory location, or it is also transferred to an output device. An execution of an instruction, I can go and perform any one of these four operations. That means a transfer of data between a registers, or between a register and ALU. And the second one is doing of either arithmetic operation or a logical operation. And number 3 is reading data from either a specified memory location or from a specified input device. And the fourth one is transferring of a data to a specified memory location or specified output device. In the execution of an instruction, I can do any one of these four operations. So that is an important thing. And register transfers. How we are transferring a data between internal registers as well as internal register to ALU. So in that case, I can go and explain this with the help of this particular diagram. So here I have a register, that is a register Ri, and I have a register Y, and I have a register Z. I have 3 registers. If you are observing this register I, here I have 2 controls logics exist. One is at input side and second one is at output side. That means if I want to transfer the information from this internal bus to register Ri, it is only possible through like this. And similarly, if I want to transfer the content of register R1 to my internal bus, only this is the path. But here the important thing is that these are 2 control logics are controlled by 2 control signals. One is Ri in and second one is Ri out. Your register name is Ri, that's why don't confuse Ri, that is a register name, in, that is copying a data into a register Ri. And second one is Ri out, that means register name is Ri. I have transferred a data from register Ri to an internal bus, then I can go and use a control signal Ri out. So if I want to copy the data which is available on this internal bus to register Ri, I have to go and make this Ri in is equal to 1. If I make this Ri in is equal to 1, this control logic circuit is active, or this switch, let me connection, this is a switch. This switch can be closed, then the data what is available on this internal bus was copied to a register Ri. In a similar way, if I want to transfer the content of Ri to an internal bus, then I can go and make Ri out is equal to 1. If I make Ri out is equal to 1, again here this control logic, just you can assume a switch. The switch can be closed, then the content of this is register Ri was placed onto this internal bus. And the second thing is, if you make Ri in is equal to 0, Then the switch was open. There is no chance for transferring of data from this internal bus to register RI. And similarly, you make RI out is equal to 0, then the content of RI is not transferred to internal bus because here the switches are open. Let you can assume this control logic is a switch. I can give you more clarity about this. This is my register RI. This is my register RI. Here I have an internal bus. This is my internal bus. This is my control logic. Here there is also a switch. This is my control logic. That is this. This is my X. And similarly, here again I have such type of arrangement. It is like this. Again this is X. Now you can assume this switch can be controlled by a control signal RI in. And again this switch was controlled by another control input RI out. Right? Then the data was copied onto this register RI from an internal bus through this path. It is like this. And data of RI was transferred to the internal bus like this. So here I clearly told you that this RI in is 1. This switch was closed. Then the data available on this bus was simply transferred to register RI. And similarly, this RI out is equal to 1. This switch was closed. The content of this RI was transferred to internal bus. If I reverse the logic, that means if I change RI in is equal to 0, the switch was open. Once the switch was open, there is no contact between this internal bus and the input of RI, so that whatever the value already exists in RI, it keep it as it is. And similarly, if I make this RI out is equal to 0, the switch was open, there is no chance for transferring of this RI value onto internal bus. So it is a more secured one. In a similar way, if I want to copy something onto Y, I took the help of this YIN bit is set to 1, then and only the available information on this bus was copied to register Y. There is no chance. Otherwise, if you make YIN is equal to 0. In a similar scenario, here is Z case also. This is my Z register. This Z register is filled with the data, which is an output of ALU. It is only possible once Zin is equal to 1. Otherwise, it is not possible. And again, if you want to send the value what is exist on Z onto the internal bus, again I have to go and make this control logic circuit is active. It is active only when Z out is equal to 1. So with the help of these control logics, I transfer data between our registers and an internal bus in most secured way. So that is an important thing you have to remember. And the same register transfer I am going to explain by considering a single bit of a register. By considering a single bit of a register. We know that a register is nothing but a group of flip-flops. By considering a single flip-flop, how I can do this data transfer. So see here guys, this is my edge triggered D flip-flop. Generally this is positive edge triggered D flip-flop. So because this arrangement represents that is a positive edge triggering, and this is your D flip-flop. So the data was entering into this D flip-flop, that is comes from a multiplexer. This is a 2x1 mux. This mux can be controlled by RI in. So previous case I see RI in register. So RI register, that RI register is loaded with some value only when RIN is set to 1. So if this RIN is set to 1, then in this multiplexer this input was selects. What this input is? This is the bus line. So whatever the internal bus I have, that bus line was connected as an input 1 of mux, and whatever the data here I have a get, let I assume that is some X. That X was reaches to the output of mux. This X input is accepted by this D flip-flop only at the rising edges of the clock, the same thing it will be transferred to an output. Then I can say that this particular positive edge triggered D flip-flop can hold the value X. That X value I was received from an internal bus. Later, if I was transferred this X onto the internal bus, again I took the help of another control signal which is RI out. So this is RI out, and see guys, this is a tri-state buffer. We know that this is a tri-state buffer. This buffer transferred the input value to output only when this buffer was enabled. That means this RI out is set to 1. If this RI out is set to 1, then whatever the value that was present at input side, which is X, that is simply transferred to output side, that X, that is goes on again an internal bus. So if it happens, this is a scenario, once here this multiplexer select line RIN is equal to 1. What happens if RIN is equal to 0? If RIN is equal to 0, this multiplexer selects 0th input. What is 0th input? This 0th input is nothing but the output of my D flip-flop. So it is fed back to the input of here. So if this RIN is equal to 0, that means your register RI, it didn't receive any data from an internal bus. It didn't receive any data from an internal bus. So that I make RIN is equal to 0. If RIN is equal to 0, this multiplexer selects 0th input. That means whatever the data already exists in that particular register, it keep it as it is. So that here my D flip-flop can hold an X. That X is again fed back to here. The same thing it sends to an output of multiplexer. And once this D flip-flop receive positive edge triggered clock, then it will accept that input and it will be transferred to an output. And one more thing, if you make RI out is equal to 0, this RI out is equal to 0, this tri-state buffer was operated in a tri-state. That means this was a logically disconnected state. That means there is no switch connection between this to this. The switch was opened so that the output of flip-flop command goes to the bus itself. So in that occasion, we are not transferring any value from register RI to an internal bus. So I hope you understand how the data was transferred from a register to an internal bus, or from an internal bus to a register in a more secured way. So with this, I close my topic. I hope you understand the fundamental concepts. That means how my CPU fetches an instruction from the memory. In that case, it took the help of two registers. One is a PC and second one is IR. We know the functionality of PC and we know the functionality of IR. And later we can go and see the data path of your CPU by considering of a single bus. So later we discuss about what are the different operations that can be performed in the execution of an instruction. In that case, our processor can perform 4 different operations in execution of an instruction that we discussed. At the end, we are seeing a register transfer, how our data was transferred from a register to an internal bus, or from an internal bus to a register with the help of some control signals or control mechanism. We are doing that. At the lowest level, how we are transfer a specific bit from an internal bus to one of the flip-flop of an internal register, as well as how we are transferring a data from a flip-flop or one of the register, a least significant bit or most significant or any bit of a register, how it will be transferred to an internal bus with the help of control signals that we discussed. So I hope you understand the concept. In the next class, we will go and discuss some other important topic as well as interesting topic in this processing unit. Thank you for patient listening. Have a nice day.